Welcome to the e-lectures for diploma students. In today's lecture, we are going to see some of the terminologies normally we use in a three-phase system. Already in the last lecture we have seen the definitions of a phase voltage. Now we will go on to the definition of a line voltage. A line voltage is a phasor difference between the appropriate pair of phase voltage. Thus VRY is a phasor difference between VRN and VYN, or the voltage between any two phase terminals of a three phase system is known as line voltage, and it is represented by the term VL. Now if you look at the phasor diagram, you can see here this VRN, VYN and VBN are equally placed. So the angle between VRN and VYN is 120. Similarly, the angle between VYN, VBN is equal to 120. Angle between VBN and VRN is equal to 120. So they are equally displaced. So which means that all the phase voltages VRN, VYN and VBN are balanced voltages. Now what I am going to do right now is I am going to find out VRY, which is the line voltage. So what is VRY? It is VRN plus minus VYN. So that is the meaning. So what is VYN? So this is VYN. So whenever you want to have negative of VYN, so you draw one more phasor like this, which is 180 degrees out of phase with VYN, that will be minus YN. So I am designating this as minus VYN. Now I can add vectorially, I can add this VRN and VYN. How can we add? We can apply parallelogram law vectors. So I will make dotted lines parallel to this VRN from VYN. Similarly, I can draw dotted lines from VRN parallel to VYN. So you can, I will once again repeat, to add VRN and minus VYN vectorially or phasor addition. So I am going to apply parallelogram law vectors. So this VR from VRN, what I am going to do is I will be drawing a parallel line to this VYN. Similarly, I will draw a parallel line to this VRN from minus VN like this. So both the lines will meet at a point, I can name that as a VRY. So I can connect this 0 with, that is O with VRY, you can get the line voltage straight away. Similarly, you can suppose if you want to find out the line voltage VYB, how can we find out? So what you can do is you can add VY and minus VYN minus VBN. So how is it possible? VYN is already there. Where should I get minus VBN? So this is your VBN. So extend this. Similarly, draw a parallel line to this. So the space is not here, I can illustrate VBR. So which is equal to VBN plus minus of VRN. So this is your VBN. So what is minus VRN? So this is your minus VRN. So this is your minus VRN. Now I am going to get VBR from VBN and minus VRN. So from minus VRN I am going to apply parallelogram law vectors. So what I will do? I will mark dotted lines parallel to this VBN. Similarly, from VBN I will draw a straight line parallel to VRN, both will meet at a single point. So I can draw that, I can name this as VBR. So, this is how I can find out all the line voltages. One is a VRY, the other one is a VYB and VBR. So, all the line voltages can be easily found. Suppose if all the phase voltages are balanced and equal, then these line voltages will be balanced and equal. What is phase current? The current flowing through any one of the phase windings of the system is called phase current and is denoted by the term I suffix ph. What is line current? Line current means the current flowing through the AC supply lines and it is denoted by I suffix L. Concept of balanced and unbalanced load. What is the meaning of a balanced load? The balanced load is a load in which each phase has identical impedances, that is, each impedance has the same magnitude and phase angle. Hence, each impedance draws equal current and power factor. Say for example, suppose if I have 3 phases, so they are connected in a star circuit. So, this is R, this is Y and B. Suppose if this impedance is 4 plus J5, if this is 4 plus J5, this is also 4 plus J5, then I can very well say that this is a balanced 3 phase system, balanced star connected 3 phase system, because all the phases have same, that is equal value of impedances. Similarly, suppose if R phase has 3 angle 20, Y phase has 3 angle 20, B phase has 3 angle 20, that is all are represented in, all the impedances are represented in polar form. This is rectangular form, this is polar form. So, suppose if everything is going to be same, then I can say the system is balanced one. So, whenever here you can see here, hence each impedances draw equal current and power factor. So, whenever the impedances become equal, then the currents drawn by the respective phases will be equal. What is the meaning of an unbalanced load? The unbalanced load is a load in which each phase has unequal impedances, that is, each impedance has a different magnitude and phase angle. Hence, each impedance draw unequal current and power factor. Say for example, if R phase has 2 plus J3, Y phase has 3 plus J4, Z phase, that is R, Y and B phase has 4 plus J5. So, all the impedances are entirely different, all are not equal. So, in this case I can say that it is very clear that the system is an unbalanced one. So, the unbalanced load is a load in which each phase have unequal impedances like this. Methods of 3 phase connection. It is a very important topic in this unbalanced 3 phase system. So, in a 3 phase alternator there are 3 independent phase windings or coils. Each phase or coil has 2 terminals, one is a start one, the other one is a finish one. The coil ends are interconnected to form either a star network, we can represent this like this Y, and delta is represented like this in the form of a triangle connected 3 phase system. Methods of 3 phase connection. In a 3 phase alternator there are 3 independent phase windings or coils. Each phase or coil has 2 terminals, one is a start and finish. The coil ends are interconnected to form either star or delta connected 3 phase system. So, this is a typical example of a star connected network. You see here, so this is R phase, this is Y phase and this is Z phase. How they are connected? You see here, so this is R phase, Y, this is B. So, all the similar points, start points are shorted like this, and the other points, that is finish points, this is start point of the phases, So, this is a finish point, this is a finish point of B phase. So, the finish points are taken out to form, this is R, Y, and to form a network called as star network. So, this point, this particular point, so this can be rearranged like this. So, and taken out like this. So, this is R, Y and B. This point is called as what? Neutral point N. So, this point is a neutral point. So, between the phase and the neutral, when you measure the voltage, so this is your phase voltage. What is the phase voltage in a star connected network? You should measure the voltage between the phase and the neutral. So, that is called as a phase voltage in a star connected network. What is the meaning of a line voltage? Where it is being measured? So, whenever you connect the voltmeter between R phase and Y phase, between these two, it is called as line voltage VL. Similarly, Y and B, if you measure, it is a line voltage. Similarly, if you measure voltage between R and B, it is again a line voltage. Between Y phase and neutral, it is phase voltage. Between B phase and neutral, it is a phase voltage. In star connection, similar ends of the 3 phase windings are joined together within the alternator, and 3 lines are run from the other free ends as shown in the figure. The common terminal so formed is referred as the neutral point, as I said earlier, or the neutral terminal. The terminals R, Y and B are called the line terminals. The voltage between any line and neutral point is called the phase voltage, VRN, VYN and VBN, while the voltage between any two lines is called the line voltage, VRY, VYB and VBR. The current flowing through the phases are called the phase currents, while those flowing in the lines are called the line currents. So, this is one more connection by which you can have a 3 phase system. So, this is called as a delta connection. You have phases R, Y and B similar to star, but the way in which the start and end points of each phase are connected is entirely different in the case of delta. So, if the start end of one winding is connected to the finish end of the next and so on until all 3 windings are interconnected, the result is the delta or mesh connection. So, say for example, this is start is A, finish is B, start is A, finishes B, start is A, finishes B. So, the start end, this is the finish end of this particular phase. So, this B is connected to A, again this B, that is end point of this phase is connected to the starting point of the other phase. Similarly, the end point of this phase is connected to the starting point of other phase. Hence, in delta connection, dissimilar ends of the phases are joined together to each other to form a closed mesh. So, you can see here, so there is a closed mesh here. Unlike the star connection, there is no closed mesh, they are connected to a single point called as neutral. Here you have a closed mesh. Here there is no common terminal, hence only 3 line voltages VRY, VYB and VB are available. So, here since you have no common terminal like neutral, here VRY, VBY and VBR are the line voltages of the delta connected network. Here there is no phase voltage kind of a thing. So, here phase voltage is equal to line voltage, both are same, is equal to line voltage. Unlike your star connected network, both phase voltage and line voltages are entirely different. here both are one and the same. Now let us move on to the relationship between the line current and phase current, line voltage and phase voltage in a star connected system. In star connection, the three phases are joined together to form a common junction neutral N. N is the star point or neutral point. When three phases supply feeds a balanced load, the current in three phase conductors will be equal in magnitude and displaced 120 degrees from each other. So, this is a very important point. Whenever the impedance of each phase is going to be same, you can expect this 120 electrical degrees displacement between each phase. Whenever it is not, then you cannot expect the same 120 electrical degrees phase shift between any two phases. It may be more than 120 or at sometimes it may be less than 120. So, this is the star network, star connected network. So, you have three phases R, Y and B. ERN is the phase voltage, EBN is the phase voltage, EYN is the phase voltage here, VRY is the line voltage, VYB is the line voltage, VBR is the line voltage. So, what is IR? IR is the line current, IY is the line current and IB is the line current. Now, you can see the phase diagram from which how the line voltages are being derived from the phase voltages. We have already seen that for a single line voltage. Now, we will see for all the three voltages. So, VRN, VYN and VBN all are displaced equally by 120 electrical degrees. So, VRN is over, VYN is over and VBN is over. Then we need to mark the respective line currents or phase currents. Here the phase current is same as the line current in star connected network. So, always we have the current IR, IY and IB lagging behind the respective voltages. You can see here VRN, if you notice IR will be lagging behind this VRN. Similarly, VYN will be leading the current IY, you see here. So, VYN is leading the current respective phase current IY by some angle. Similarly, VBN, IB. So, IB will be lagging behind VBN, yes, you can see here. So, once you rotate the phasor in the anti-clockwise direction, you can come to the conclusion that this VBN is clearly leading the voltage IB, or IB is lagging behind the respective phase voltage by some angle. IY is lagging behind the respective phase voltage by some angle. Similarly, IR is lagging behind the respective phase current phase voltage VRN by some angle. So, this is over, all these phasors are represented. Now, what am I going to do is I am going to find out VRY. So, how to find out VRY? VRY is nothing but it is a vectorial combination of VRN and minus VYN. So, how can I draw this minus VYN? So, this is your VYN. So, whenever you draw a straight line anti-parallel, that is exactly out of phase with VYN, so it will be minus VYN. Now, it is very simple to add the two phases minus VYN and plus VRN by applying parallelogram law of vectors. How to get VRY? So, from this starting point, this point of VYN, so a parallel line is drawn to VRN. From VRN a parallel line is drawn to minus VYN. So, both the lines will intersect at one point which is called as VRY. So, draw a straight line from 0, that is origin to VRY. So, that will be your corresponding phase voltage. So, this phase voltage, the angle between VRN and VYN, VRN and VYN is 120. So, angle between VRN and minus VYN will be 60. So, this you can see here from the phasor diagram, it is quite evident that this particular phasor VRY bisects V minus VYN and plus VRN. So, the angle between VRN and VRY will be 30 electrical degrees, 30 degrees. So, the angle between, so the very important conclusion what we derive from this phasor diagram is the angle between the phase voltage and the line voltage VRN and VRY is 30 electrical degrees. So, this is what we derive. Now, let us move on to the next line voltage calculation, which is VYB. So, what is VYB? VYB is equal to Vy, that is VYN minus or plus V minus of VBN. So, one is VYN plus minus VBN. So, this is your plus VBN. So, you draw a phasor like this, which is represented as minus VBN. Then you apply parallelogram law of vectors. So, draw a parallel line to this VYN. From minus VBN you draw a parallel line. Similarly, from plus VYN draw a parallel line to minus VBN. Both will intersect at one point, you name it as VYB. So, it is one of the line currents. So, from O you draw the straight line joining O and VYB. Now, you can see that the angle between this angle, the angle between VYN and minus VBN will be 60 degrees. The angle between VYN and VYB will be half of that, it is 30 degrees. So, in R phase also the angle between VRY and VRN is 30. Here also the angle between VYN and VYB is equal to 30 electrical degrees. So, we found out VYB also from the phasor diagram. Now, it is time for us to calculate VBR. So, what is VBR? It is a combination of VBN plus minus V or RN. So, VBN is here, yes, VBN is here. What is minus VRN? So, here is VRN. So, you draw a straight line here. So, it is minus VRN. Now, we are going to vectorially add by applying parallelogram law of vectors. So, draw a parallel line from minus VRN to VBN. So, this is a parallel line to VBN. Similarly, from VBN draw a parallel line to minus VRN, both will intersect at one point, you name that as VBR, it is the third line voltage. So, you draw this, draw a straight line to the origin O. Now, you can see here VBN and V minus VRN, what is the angle? It is 60 degrees. What is the angle between VBN and VBR? It is 30 degrees. So, in all the cases the angle between, so this is the conclusion what we can derive at by seeing the phasor diagram. In all the cases, this case and this case and this case, in all the three phases, the voltage, sorry, the angle, phase angle difference between the phase current and the respective line current is 30 electrical degrees, which means that the line current is leading the phase current by 30 electrical degrees. Now, what is line voltage and phase voltage? The potential difference between any two line terminals is the phasor difference between the potentials of these terminals with respect to the neutral point, as I said earlier. So, since all are balanced loads, we can take this VRN is equal to VYN is equal to VBN is equal to V phase, a common terminology V phase has been introduced here. What is VRY, VYB and VBR? These are termed as the respective line voltages. As a single notation VL, we can represent all the line voltages VRY, VYB and VBR. So, what is the potential difference between lines R and Y? It is VRY is equal to VRN plus VNY or VRN minus VYN. Similarly, potential difference between lines Y and B, it is VBR is equal to VBN plus VNR or VBN minus VRN. From the phasor diagram, we can state that VRY is equal to VRN minus VYN. So, what is VRY? It is 2 into V phase into cos 30. VRY is equal to 2 into V phase into root 3 by 2. VRY is equal to root 3 V phase. So, this is a very important conclusion what we can derive. So, VRY is equal to root 3 into V phase. Always in a star connected circuit, phase voltage is root 3 times the line voltage. So, this is the impression. Similarly, we can derive VYB is equal to VYN minus VBN, which is equal to root 3 V phase. VBR is equal to VBN minus VRN, which is equal to root 3 V phase. So, VRY is equal to VYB is equal to VBR is equal to VL, which is the line voltage. So, in general we can generalize this in a balanced star connected circuit. So, this VL will be equal to root 3 times the phase voltage. Now, let us have a quick recap of whatever we have dealt in this particular lecture session. So, we have analyzed the 3 phase systems, that is in what fashion a 3 phase system can be connected, either a star connected network or a delta connected network. We have seen the advantages of 3 phase systems, and we have seen the phasor diagram. We have analyzed the phasor diagram of a balanced star connected network, and we have derived the respective expression of line voltage in terms of phase voltage. Thank you.